Greetings, everybody, and welcome to the 2016 African Sustainability Summit. I am Yaw Agbede, and this is the third session dealing with Nsukora, which is rainwater harvesting. So let's get right into it. Previous sessions, we've talked about who we are in Kala Environmental, as well as myself, Yaw Agbede, give our perspective on African sustainability, and we've talked about our design approach at Incala, indigenous knowledge and appropriate technology for endogenous development. In the previous two sessions have already been covered. So in session one, the roots, we dealt with the overview of rainwater harvesting, some of just the main fundamentals of rainwater harvesting, as well as some basic talking points to keep you engaged in the conversation. In session two, we went over the sprouts, and these are design considerations for rainwater harvesting. So we looked at things such as water quality and issues like mosquitoes, things like that that people tend to think about in rainwater harvesting. Now we're moving into session three, which is the hardy session, which we will get into some actual design calculations for a rainwater harvesting system. So let's get right into it. So rainwater harvesting design calculations. One of the things that we've said in previous sessions is that why are we using rainwater harvesting in the first place? Well, a lot of it has to do with the situation where in many cases rainwater is the only acceptable source of water for a community or for a household. And so we're looking at water in that context. We don't have other sources that are available to us. So in designing rainwater, there are several steps that we have to take, or best practices that we should take. In preliminary planning, there are some basic questions that we want to ask before we go into design or building of our rainwater harvesting system. The first question is, are there adequate resources available? So if you're building a rainwater harvesting for your family, or perhaps you're a part of a community and you're building something for your community, that should be the first question that you ask. Are there resources available? Do you have the money, the manpower, and so forth to finance and to actually build the system? The second question is, what is the most effective cistern design? And this depends a lot on your context, the size of your cistern, as well as the size of your wallet. So these are some planning questions that, again, as you see in this picture here, we have a group of Africans meeting on this topic and trying to determine the answer to these questions. The next we're looking at is how much available space is there for building a cistern. So for us, we're not limited per se by space. We're in the rural area, we're in the bush, but you don't necessarily want to have your compound become overrun by your rainwater harvesting system. So you have to decide how much space you're willing to dedicate to your rainwater harvesting system. And finally, the last question you need to ask is, what is the capability of the people who will be using the system to maintain it? That just means basically cleaning the tank and the gutters and disinfecting it periodically. And water quality depends on that maintenance of the tank. So we haven't talked a lot of specifics about the quality, water quality aspect of rainwater harvesting for consumption, but you do need to have a level of treatment for your water that you harvest from your rainwater harvesting system. But the level of treatment that's required really depends on you. It depends on how much you maintain the system, how clean you keep the gutters, and those types of things. So that's a very important question. Having a committee that's responsible for maintaining the rainwater harvesting is not a bad idea as well. Okay. These are preliminary questions, and the main thought here, if we want to differentiate rainwater harvesting from other types of systems of water supply, such as boreholes or intakes from the river, or so on and so forth, rainwater harvesting is very much an off-grid technology. What I mean by that is a lot of the responsibility for the system is on the individual household. So oftentimes you have a rainwater harvesting system and it serves one household, maybe two households. And those one or two households are responsible for the system, as opposed to a community-wide or a village-wide system of water supply. So that's a very important concept there. So getting into some of the preliminary planning criteria for rainwater harvesting, as we talked about in other sessions, we have to look at the roof materials. And roof catchments, of course, we know are only suitable for certain types of materials, such as tiles, slate, corrugated plastic, or corrugated metal sheets. All right, so those are the materials that we want to make sure we have access to and that we are considering as a part of our designs. We want to make sure we're not looking at rainwater harvesting for thatch roofs or roofs that have been painted or lead roofs or any other type of roof that would contaminate our water supply. So that's very, very important. And if you're doing your rainwater harvesting system as a part of a retrofit, meaning the house already exists, as opposed to if you're building a house, if you're actually building a house from scratch and thinking about rainwater harvesting at the same time, a couple of things to consider if you're looking at, say, slate or tiles versus sheet metal roof is that the weight of the sheet metal is lighter. And so that means that your roof truss, your roof structure doesn't have to maintain as much weight. So either option is very good. It depends on, of course, your budget. It depends on what you like best. All right, continuing on, the most important topic for rainwater harvesting, of course, is water availability. And what we see here is a hydrograph from the capital of Togo, of course, a neighbor to Ghana. And a hydrograph basically shows the level of precipitation. And this particular hydrograph shows, I think it shows some other things, some temperature and relative humidity and daylight hours and so forth. But this basically is just showing, this is a precipitation chart. So it's showing us how much water is expected, is average. Okay, this is statistically based in this particular area. So the way we read this, if you look at this green line here, this thin green line, this is basically giving you the trend of the number of wet days, and of course the green bars actually represent the precipitation, the amount of precipitation in millimeters. And what you see for this part of Africa is you basically see two peaks, one large peak around May and June, and then a smaller peak around September and October. So what that's telling you is that there are two wet seasons, there are two rainy seasons, or two dry seasons, depends on how you look at it, in this particular region. And so that becomes important as we look at our water availability calculations. So this is the monthly rainfall data that you can access by searching on the internet. You can go to your local Ministry of Agriculture or any other place like that. You have a weather service, airports, and so on and so forth. But you can find monthly rainfall data estimates. And if nothing else, you can talk to elders and get a general idea of what the wet weather trends are like for the area that you are designing your rainwater harvesting system. But that's a very important thing to be able to find that data and to interpret it. So this is one format that you might see rainfall data in. So let's look at an example. Let's say we're in a particular region where we get 800 millimeters of rain a year, which is about 31.5 inches a year. And we're trying to collect rainwater from a building that has a footprint of 6 meters by 8 meters. And we want to know how much rainfall can we collect. So this is a calculation that was introduced in the previous session, so we're just kind of doing a review here. And we're using the equation that the volume of rainfall is equal to our runoff coefficient, which here we're using 0.8. I think in the previous session we used 0.85, so here I'm just being a little more conservative. So it's our runoff coefficient 0.8 times R, the amount of rainfall in millimeters, times A, the projected area of our roof. So to find the available rainfall for this location, we're going to substitute our values into this equation. So we say 0.8 times 800 millimeters times 48 square meters, and that's 6 meters times 8 meters gives us 48 square meters. Now multiply all that out, that gives me about 30,720 liters per year, which is how much rain I can expect to fall on my roof and to be collected by that roof system, including evaporation and other losses per year. And further, we can take that calculation further and divide that by 12 months in a year and get that on average, we would expect about 2,560 liters per month. And then we can go even further, divide that number by 365 days in a year, and that tells us that we can expect about 84 liters per day. All right, so this is a calculation that's telling us this is the amount of rainfall. Again, this is the average, but this is what we use to design our system, that we can expect about 84 liters per day. In theory, if we could collect all of it, that's how much we could get for our location based on the size of our building. Okay, and that equates to about 22 gallons per day. So a good amount of water from not the largest building, 6 meters by 8 meters, not the largest building in the world. We can get a large amount of water. Now, the assumption here that we'll get into a little bit later is that this is a steady amount of rainfall, that we get, 30,720 liters per year, and it's essentially a steady flow of rain. Every month usually gets about the same amount of rain, which, based on the precipitation chart on the right, we see that for this particular location in Togo, that's not the case. That there's rainy season and there's dry season. And you can see that June gets a lot more rain than January does, or December, or November, or February does. And so that becomes a challenge when we're looking at rainwater harvesting systems, so we'll get into that and see what we can do about that. All right, so continuing to talk a little more about water availability. So that was water supply. That's how much water is available to use. The other thing that becomes important is water demand. How much water are you using as a household? And this is one of the things that is crucial and important for any type of so-called green technology that you get in, that the first step of it, whether it's rainwater harvesting or using solar photovoltaics or whatever, is the first step to implementing those is conservation. That especially if you're raised in the West, if you're raised in Europe or America, or you're raised to be Western, wherever in the world you are, if you're raised to be Western, then you are wasteful and you consume a lot of resources. And so there is the very, very important need to learn how to conserve it. So that becomes the first step in designing these a rainwater harvesting system in particular, but any green technology in general, is conserving whatever resource you're looking at, whether it's water, whether it's energy or sulfur or whatever. So here is a value that we have, the minimum requirement of water for a person, about 15 liters per capita per day. So that's 15 liters per person per day, which equates to about 4 gallons per person per day. So we take that as the minimum amount of water that a person needs to meet their needs. All right. So minimum 15 liters per day, or 4 gallons per day per person. Now, let's look at that same example. Let's continue it a little further. So again, we have the same scenario, 800 millimeters per year of rain, a 6 by 8 building, 6 by 8 square meter building. We just calculated that we expect 84 liters per day, and we want to know what that means for a household of 5 people. Okay. Well, what we have to do is we take our 85, or I just rounded it up, 84 became 85. So our 85 liters per day, we divide that by 5 people, and that gives us a water demand of 17 liters per capita per day, or 17 liters per person per day, which is okay, because that is more than the minimum requirement. So that means that should be enough water to meet everybody's needs. For this system that we're just looking at, 800 millimeters of rain per day, that gives us an available 17 liters per capita per day. So that means that everybody can have at least that minimum of 15 liters per person per day. Now, what happens if we have a household of 6? for this same scenario? Well, if I take my 85 liters per day and divide it by 6 people, then you see that it only gives me 14 liters per person per day, which means that for a household of 6, this system is too small, that we would need to do something else in order to meet our needs for this size footprint, for a 6 by 8 footprint. Okay? So perhaps we install rainwater harvesting on a shed to give us an additional volume of capture. So that's a very important concept. Now, what we were just talking about is this calculation that we've just done assumes an even distribution of rainfall. That if rainfall is evenly distributed throughout the year, then the general rule that we use is that the cistern has to be large enough to store 1 month of water supply. All right? And so in this example, we calculated it was 2,560 liters per month. That's what's available to use. So if we thought back to the previous slide, that's how much water per month we can expect. And so therefore the cistern for this system should be about 2,500 liters or 2,600 liters. Okay, so we get into that when we're talking about storage. I think I'm getting ahead of myself. So when we talk about storage, we've already talked about the different types of tanks that we can have. Reinforced concrete tanks, clay tanks, plastic tanks, so on and so forth. And the size of these tanks, it depends on several things. One, of course, it depends on the amount of water that's needed. It depends on the amount and the frequency of the rainfall. It depends on the size of the roof surface, and it depends on the cost. And so, again, I was getting ahead of myself. Back to that previous example where we have 2,560 liters per month, assuming a steady distribution of rainfall. Then what that means is that if I convert liters into cubic meters, that's 2.56 cubic meters per month. And so that means that that is our required cistern capacity, because that will give us a 1 month supply of water, right? Which is what we need to take us through the year. So that's how we would size our tank. Okay? It's based on the amount of available water that we can store in our area in a 1 month period of time. But again, that assumes an even distribution of rainfall. So if you do not have an even distribution of rainfall in your location, in many places, tropical places do not, then we have to look a little bit deeper, which we'll get into here in a second. So what do you do in that situation where if you don't have that steady flow of rainfall, where you have rainfall that is heavy during some months, which we call it the wet season or the rainy season, and then it's little to no rain other months of the dry season? What do you do? Well, the basic idea is that you have to store water during the wet season for use during the dry season. So you store more water when it's raining, and you use that water to carry you into the season when it's not raining. All right? And so what that means, of course, is that you need a larger tank. So if for our previous example, if you weren't in an area that had a continual or had an even distribution of rainfall, then that 2.5 cubic meter tank or 3 cubic meter tank would not be sufficient for your rainfall needs, because water is not going to be steady like that. You would need a larger tank so that you could store more water during the rainy season and use that extra storage during the dry season. But the issue with that, of course, is that a larger tank is more expensive. And so in some cases, depending on the various circumstances, this can make rainwater harvesting a bad choice for you, depending on the severity of your dry season and the duration of your dry season. Okay? So for example, you have a 3-month-long dry season. That means that you need 3 months of additional storage, right, to use that you have to capture in the wet season. That's 3 additional months of storage that you need. And so what that means is a very, very large tank, maybe 3 times as large. And so that means the cost is going to shoot up as well. And for a lot of people, that's just not feasible. But there are alternatives. All right. And one of the alternatives you see in the picture here is rather than having one huge tank, is to have several smaller tanks or several cheaper tanks. So locally, you can have clay tanks made for a very, very, very inexpensive amount of money. You can have other types of smaller containers and invest in several of them, as you see here. Um, the challenge with this type of system is that it requires is much more of a hands-on system. You have to actually be there operating it, so to speak, when it's raining, because when this jar fills up, this jar here fills up, you have to move the downspout to the next jar. You have to move the next jar under the downspout, and so on and so forth. And so that might not be something that you can easily do. And of course, there are overflow systems and all types of things you can do to automate that. But a very simple system like you see here is going to require much more hands-on type of activity. But the advantage is that you get to save in costs as opposed to a very large tank. Another alternative is, rather than trying to have a system where you're trying to supply all of your needs or even most of your needs with rainwater, you can use a potable water only system where you're only using potable water, or you're only using your rainwater to drink and to cook with, maybe to, maybe a little bit of personal hygiene. All right, and so you're only using it to drink and cook, and you're using other water source to wash your clothes and bathe. And a lot of people don't realize it, but you need a certain level of purity to drink water, to cook with water, but you do not need that same level of purity to wash your clothes, for example, or to bathe your body. So washing your clothes in the river, or bathing in the river, or bathing with river water is perfectly fine. All right, there's nearly no need to treat that water beyond the level that it's already treated, just to wash your clothes, or just to take a bath, right? But of course, when you're brushing your teeth, or if you're using the chew stick, or if you're cooking, drinking water, things like that, you definitely want to have water that is of a higher quality. So a potable water only system means that your demand of water is lower. So therefore, you don't need as large of a tank to satisfy that smaller demand. Another option that we talked about in the previous session is a wet season only system, where you only are designing the system based on using it during the wet season, so that you can not have to worry about having to go fetch water or whatever during the wet season. So that becomes another option if a large season a large system to take you through the year is too expensive. Okay, so those were some preliminary design considerations. Now we want to get into the actual design of a rainwater harvesting system and what that looks like. So a couple of things that we want to do in our design: we definitely want to have some design drawings. This is a profile drawing where we're looking at it as if we're standing on the ground. It would also be a good idea to have plan drawings, which is basically like a bird's eye view, looking at everything from the sky, looking down. And the purpose of these drawings is to replicate the system and to allow you to see conceptually where everything will go. So in this system, we have all of our components labeled here. It would also be a good idea to add the dimensions of all of our piping and all of our storage tanks, so we have the correct scale, so that we understand what size everything is and how much of everything is. If we're buying pipe, then we need to know how much pipe we need. And so creating design drawings to scale helps you to figure those things out. So this system is showing basically everything that we would need for our system. So we see our gutters here connected to some type of T, and this is our first flush system with the clean out, so that when the first flush of water comes, it's captured and stored here, and after the rainfall, we release this plug and let it come out. And of course, after the first flush, the clean water is allowed to go into our storage tank as follows. And so it can fill either from the bottom or from the top, depending on how we want it to do. And you see you have a spigot here, you have another spigot here. So this is for withdrawing water from the tank. And you can also hear this, you have this bottom valve, so this is, we can keep it open during normal operation. If we need to close it, if we need to empty the tank, it's there. So you see all of these, and you see the overflow valve, which of course is very important. So if you get the tank is full, it doesn't back up into your gutters and start causing problems there. It just overflows. However, so this is a very important aspect of your design, is having drawings to represent the things that you plan to do. Label, dimension those drawings, and be as detailed as you need to be in order to convey that design. Even if you're building it yourself, but especially if you are having someone build it for you, you want to be able to communicate very clearly what you're looking for, and so forth. So design drawings are very important. Next, you want to create a materials list of the different things that you will need to actually build this thing. This is from the perspective of the contractor, or from the perspective of who is actually going to build it. So we're assuming that's you. So you're going to, need certain things. You're going to need labor, right? We're African people. We don't do things alone. So you're going to need some hands, some folks to help you. And depending on the size of your system, you may invest in a foreman, which is basically someone who organizes the labor, the day laborers. You're going to need people who are laborers, people who are basically just muscle, who can come and move stuff, and who can connect pipe, and who can dig, and who can pour concrete, and things like that. So you need the laborers, but then you also need the person who is in charge of the laborers, who's more of the expert, and who is able to guide people who are less skilled. And the logic behind that is that the foreman is more skilled, he has more experience, he's also more expensive. So if you're paying him for his expertise, you're only going to really want one of him, because he's going to be more expensive compared to the laborers. A lot of times these are teenage boys in your area, and so you can get them and they'll work for a lot less money than what the foreman has. So you want to, for your project, depending on the size of it, you want to label, you want to come here, and in your design, you want to say how many foremen do you need and what's the estimated cost. So you can call around and ask people, how much would you charge per day or per hour to do this particular job? And the same thing for the laborers. Next, you want to look at the supplies. So what will you need? Will you need, if you're building a house, or you have a small shed that you're using for rainwater harvesting, what type of roofing material do you want to use? Are you going to use metal tiles? You're going to use plastic tiles, or metal sheets, or plastic sheets, or tiles, clay tiles? What quantity of those that you're going to need? What's the estimated cost of those things? So this is, if you're in Africa, this is going to mean you're going to have to go around to the different vendors and ask them for quotes for these types of material. Right? It's not like it's not going to be like you can go online and just search. No, you're going to have to actually go meet people and shop around physically to get those prices. So you're going to need something for the gutters. So you can make your gutters out of that same sheet metal. You can make your gutters out of wood or bamboo. I like wood or bamboo gutters. They're very pretty to me. They look good. The challenge with them is that because they're organic, they will rot. And so you have to replace them more often. So that's another consideration if you're using the bamboo or wood over the metal. You'll need wire, rope, or fiber, something to secure your gutters to your roof. You'll need some type of adhesive to make your connections to your downpipe. You need nails and wire screen, all these types of supplies. You want to make sure you detail them in the supply list. And as well, from a construction standpoint, what are the tools that you'll need? So how many hammers do you think you'll need? How many machetes do you think you'll need? And this, of course, is related to the number of laborers that you have. So you don't want to have five brothers laboring, but you only have one hammer, right? Because then you're going to be paying a bunch of people for standing around doing nothing. So you want to make sure that your tools match your laborers. Very important. So this is a general basic materials list, or even a preliminary materials list. When you get down to the real design, you actually want to get into a construction schedule or a bill of materials. And what you're doing here is you're going and putting the very, very small details of every single item. So the tank, so let's say you're using a plastic tank, an HDP tank, all right, and it's 2,500 gallons, and it's one each, so you're using one of those. So that tells you that, and so you can get the price for that. You're going to have a certain amount of downspout piping and supports and all those type of things. And perhaps you have 325 linear feet of that. You have your first flow system and your screens. You have one of each of those. You have a concrete pad that's, let's say, 5.6 cubic yards. You have a 6-inch PVC overflow pipe, and that's 120 linear feet of that. You have a lump sum price for all of your drains and your spigots and your overflow piping and all the appurtenances that are required to install those. So you go to your plumbing hardware supply and you say, what's a lump sum for all the things that I need for this project? And so on and so forth. This is your engineering construction schedule, your bill of materials. This is the detailed layout of all the materials that you need. And once you finish your materials list and this construction schedule, this will give you an estimated cost of construction for your rainwater harvesting system. So as you're doing your design, you have a general idea of what you should expect to pay for your system. And as a good general rule, any type of estimate is always good to add a contingency in there. Contingency is extra money that you put aside for unexpected things to come up. So in construction, often there are things that are unforeseen that come up, and they almost always cost us more money. So it's always better to budget that contingency, that what if money in, rather than to say, okay, this rainwater harvesting system is gonna cost me $300. And so you only have $300, and then something comes up that's another $100, and that's gonna stop you from doing the project. So it's good to already budget that in from the beginning. A good amount for contingency is 20 to 30% of whatever your estimated construction cost is. All right, the next step, if you've got your design drawings and you've got your bill of materials and your construction schedule, is based on your design drawings, you want to determine the projected roof area for the surface that will be collecting the rainwater. And we have two pictures here that are showing you how to do that. So again, when we say the projected roof area, we are meaning the area that if you were looking above, if you were looking at it from a bird's eye view down on the roof, what area would you see? So for example, if this is our roof here, even though this roof is pitched, even though this is a sloped A-frame roof, the projected roof area is actually this perfect rectangular shape just like this. Okay, it doesn't matter how much the roof is sloped. Same thing here, we have this roof which has two different types of pitches perpendicular to one another. Doesn't matter. Our projected roof area is basically just the footprint or the shadow at noon of what this roof will look like. Same thing here, doesn't matter the shape. Even this roof is rounded here, but the projected roof area is still rectangular. All right, if the footprint is rectangular, then the projected roof area is rectangular. So based on your design drawings that are to scale, of course, or your field measurements, going out and measuring the dimensions of your building, you can determine that footprint. So for this building here, you see 6 meters by 8 meters. And that's the footprint that we'll use for our projected roof area. So that becomes very important. Next, we want to calculate the volume of water that's available to us. And again, we've done this example a few times, but let's do it again to reinforce that idea. So we have 800 millimeters per year of rainfall, our same 6 by 8 meter building. We're going to find the available rainfall by multiplying the millimeters of rain times our 48 square meters. 6 times 8 is 48. And multiply that by our runoff coefficient of 0.8. And we'll get 30,720 liters per year. Divide that by 12, that gives us just under 2,600 liters per month. And divide it by 365, and that gives us our 84 liters per day. So now we know how much water is available. All right, so we've done our design drawings, we've done our construction schedule, we have calculated our projected roof area. Now we know how much volume of water we can expect that is available to us based on the size of our roof and the average amount of yearly rainfall, 84 liters per day. Okay, next, what we want to look at is the guttering. All right, and so you have to have gutters on any side of the roof that you want to collect water. If you have a pitched roof, if you have a single pitch roof, then you only need gutters on one side. If you have a double pitch roof, like the examples we've been looking at, then you'll need gutters on both sides if you want to use that entire roof area. If not, you have to adjust your roof area based on how much water you're actually catching. All right. So the gutters ideally should be as long as the edge of the roof, so that again you can catch that entire roof area. If your gutters are not the entire length of your roof, then your projected roof area is even further reduced. Okay. Let's see. Let's see. What else can we say about gutters? You also want to have a downspout, of course, and this is how we convey the water from the roof to our rain pipe. And I'm going to talk about these two figures in a second. We've already talked about metal gutters, that they're the most durable and they require the least maintenance, but the challenge with metal gutters is that they're also the most expensive. And so you can also make gutters out of wood or bamboo, and those are a lot more inexpensive, but they're not going to last as long. So it's always a trade-off there. So it's going to require more maintenance. So perhaps you're going to have to maintain your gutters more than if they were metal. Another thing to think about is, you don't want to get into too much of treating of the gutter if you're using bamboo or wood gutters. You don't want to treat them with too many harsh chemicals, because you're using this to catch water that you're going to be drinking with. So you want to be very cognizant of that as well. All right, but those are options, but it requires more maintenance, which is not a bad thing. Okay. You can install wood and bamboo gutters to overlap, and you can tie them together with rope or wire or whatever type of fiber that's available to you locally. If you use wood, of course, you need to hollow it out so that you can make it into a channel so that the water can flow. And if you're using bamboo, you want to make sure you split it, and you want all of the partitions on the inside of the bamboo to be removed. So if you slice and split open some bamboo, there are partitions, so make sure you remove those partitions so that the water can flow easily. Most important thing with the gutters, they need to be sloped. It needs to be a small slope. It doesn't need to be extreme, but they do need to be sloped so that water will flow completely through the system without pooling. That's the most important thing. If your gutters are too flat, especially if you're using bamboo or wood, that's not as it's not as regular of a shape as metal. You want to make sure you have a good slope so that you're not pooling water, or you're catching sediment and nutrients or leaves or things like that that build up and can attract animals, insects, and so forth. You want to make sure there's a good slope so that all those things can be prevented. Mosquito breeding is prevented. Talked about the downpipe. You want to make sure you seal the joint where the downpipe and the gutter connect. All right, that's very important because you don't want water leaking out through that. You want a clean connection. If you use metal, then you can seal it with caulk. Okay, if you use bamboo or something like that, you can use tar. So those are type of kind of material considerations there. We've talked about in the previous session that while it's not raining, you have all kind of debris and dust and bird droppings and insects and all these things that are attached to the roof. And when that first rain comes, all of those materials are going to be washed into your rainwater tank and increase the contamination of your rainwater. So to deal with that, of course, we have first flush boxes. All right. And so we can talk about that in a second. So we definitely want to have a mesh screen in place as a part of our guttering, first off, so that we can prevent any large debris from getting into our system, such as leaves and things like that. And it'll prevent large debris from getting through, but it'll still let water get through. But of course, because it's a screen, it's basically like a type of coarse filter, it's more maintenance, right? Because you're going to have to clean it every so often because it will get clogged. So that's very important. In the picture here, you see is the downpipe that can be manually moved away from the cistern. And so in this case, this is a simple form of a first flush system. The gutter itself is your first flush system. And the way this will work is that during the first flush of rain, you would have to manually remove this downspout and put it here where this dotted line is, so that during the first flush of water, that first flush just drains off to wherever you have your channel going. And then after that first inch of water or first gallon of water is flushed, then you can connect it back to your storage tank. And same deal here, when this storage tank is full, you can take it and move it and connect it to the next storage tank. So you have double the storage there. Of course, that again is more intensive. You actually have to drive your rainwater harvesting system as opposed to being on autopilot. You actually have to be there and be active part, which is never a bad thing. But it is more work. It is more, you have to pay attention to it. So if you're frequently away from your house, so there's frequently no one there, this might be a more difficult system to have to maintain and use and be efficient. But this is an option for you to do that. Of course, there are several other techniques that you can use for diverting. So the picture on the right, we see the first flush box where it's designed to trap that first flush of water and screen it and filter it and allow it to a lot of that sediment to settle to the bottom, and the clean effluent is allowed to flow through another screened intake, which you see here, and then finally into our rainwater barrel. So making sure that we only have the cleanest water that goes into our barrel. Once our first flush box is full, after the rain stops, we basically just open this spigot here and it drains all the water and it's ready for the next rain event. So again, you still have to drive, right? None of this stuff is like automated where you can set it and forget it. You still have to be very much a part of your system. And when it stops raining, you have to make sure you empty your first flush box, close your valve back, and you have to be very, very active in it. So that's very important. And it helps to keep you involved in the maintenance aspect of it, which becomes very important. Of course, there are other designs that you can use as well that are less maintenance intensive. But of course, typically with that, as convenience goes up, so does cost. And convenience is another topic of discussion, but convenience, I think, is one of the things that kills us as a people, as Africans, is we've been sold on this idea of technology for convenience, and that's never been the purpose of technology. It's not for convenience. We'll talk about that at another day. Okay, so what else can we say? Other types of first flush systems, you can have a filtration system where it essentially does the same thing, but using instead a filter mechanism. So this is a basic filter that you can make in the field yourself using gravel, sand, charcoal, and a mesh screen, okay, in order to keep all that stuff from falling into your tank. And it does the same thing. So the first flush comes into the box, you have a volume above, and it gives it time to infiltrate into the tank. And so it gives you a cleaner level of water quality. All right. But again, like I said, it's just like our meshes, because it's a filter. Filters require maintenance, so you'll have to replace the media or clean the media out periodically to make sure that it's still functioning properly, because it will get clogged eventually. Okay. And the last option we have for dealing with that first flush and the stuff that's coming out of the gutters is an easy device that is basically just a downspout with two outlets, and one goes to the storage tank and the other one is waste, right? So it basically goes to the drain, and you have a valve or a lever on the outside which lets you turn and determine which one is which. So this is very similar to the system we saw on the previous slide, where you just move the downspout. But instead of having to actually move the downspout, all you have to do is turn this valve, turn the lever on the valve here. So if you turn it, let's say to the left, then that gives you your first flush, so the water just goes and drains down the channel, so you can make sure that the clean water comes. When the clean water comes, you turn it back to the right, and then the water fills up for your cistern. Again, very hands-on. You have to be there and make sure you're operating this in order to use it. But again, being hands-on gives you that economic advantage as opposed to doing it for convenience. Now, the cistern, the tank. This is probably the only slightly complex, it's not really complex, but the most complex aspect of a rainwater harvesting system is how to correctly size the cistern, how to correctly size the rainwater tank. So that's a very important topic. And so we're going to get into that right now, and then we're going to look at some design calculations on a spreadsheet that I've developed. So first, let's just look at a couple of different options to give you some design ideas for what you think might be best for you. So here we have prism type rectangular profile tank. So you see it fits up at the back of the house here. It's connected by two down pipes, so their guttering is connected to both pitches of the roof, with this double pitch roof here. So we have our down pipe going into a T, into a single pipe, and into our roof washer system that we just saw. Here's the overflow for our roof washer system, and into our rainwater harvesting tank. Our rainwater harvesting tank also has an overflow, so if it gets too full, it will overflow into a trench that we have lined with stones or something like that. This is the drain valve we have here, so if we need to get water from our rainwater tank, this is where we would do it. So we can put our buckets under here, collect water. We have a manhole here, and this is for maintenance. So, every so often we need to get into our tank and clean it out and make sure that everything is nice and clean and everything's working properly in there. So we have a access hatch here. We can do that. So this is a basic good design of a rainwater tank. All right, perhaps this is concrete. Perhaps this is a reinforced concrete. Very strong design and is conducive to large rainwater tanks, but it can be expensive. All right. To the right, we have another design. Perhaps this might be less expensive, a little bit less expensive, but still on the high side. This is a ferrocement tank, and is essentially you can design it to have various types of shapes because it's essentially plastered. You're plastering the ferrocement onto a wired mesh, and so it gives you more flexibility of being able to design it. So if you want an amenity, you want a nice looking tank, and you want it to add value to your house, you perhaps could use ferrocement, which is maybe less expensive than reinforced concrete, but it can still be expensive depending on what you're looking at. But we basically have the same elements here. So we have our double pitch roof, guttering on both sides, water going sloping down to a down pipe to a T here. We've got two 90-degree bends take us into our roof washer. This is the overflow pipe for our roof washer. Into our tank, we have our washed water overflow valve, or the overflow pipe for our cistern. This is our drain valve, and we have that shallow trench, so that the purpose of this trench is to convey water away from the tank, so that we don't want the water to pond around the tank, one, because that can attract mosquitoes, and two, because that can undermine the foundation of our tank. If we have it built on a concrete slab, we don't want water getting underneath that foundation and making it change levels. So that becomes important. Here we have our outlet. All right, so the drain valve is more so of if we want to actually drain the tank for maintenance. This is our outlet of what we will use to get the water. So if we have our bucket, we put our bucket into here. This is a gravel soak away again, so that the water doesn't pond there. It just goes into and soaks into the ground naturally. And if you wanted to, you could pipe this into your house. You have a very low flow water, but you could have it piped into your house. Now, the thing about piping, if you have piped water, you use more water. Your consumption goes up automatically. I think it's about, I forgot the numbers, but I think it's about, you use about 3 times as much water simply by having it piped into your house, as opposed to having to go outside of your house and get it from a tap stand. So as soon as you pipe water to your house, you're going to increase your consumption of water, which is going to perhaps change the effectiveness of your rainwater harvesting system. So that is an option for you, but just keep in mind that if you have piped water, you are wasting more water compared to if you did not have piped water. Some more designs. This is a brick. On the left, we see a brick cistern. So a mason makes this, and we see a cross section here, and it shows us, okay, here's our access hatch. This is our overflow. So if the tank gets too full, it's able to overflow. Down here we have our valve box, and we have two things going on here. We have an inlet and an outlet, and so we have a valve that can determine that. Perhaps we have a check valve if it's an inlet, so it prevents the water from flowing backwards. It only flows into the tank, and we can reverse that check valve if we want to make it into an outlet, or these two are in parallel. Perhaps there's one pipe that's right next to it, that's the outlet, and the other one is the inlet. At the lower elevation, we have the drain, and again we have the valve for that. So during normal use, we have the valve closed for the drain. During maintenance, we open the valve for the drain, we drain the tank, and then we can go in the access hatch and clean it and do whatever we need to do. Here is the concrete foundation, of course. This looks like a pretty big tank, so it's very important that you have that concrete foundation, because water is very heavy. When you have a 55-gallon tank, that's over 450 pounds if it's full. So just imagine, if you have 1,000 gallons or something like that, that's a lot of weight, and you don't want it sinking into the ground or floating or anything like that, so you want to make sure you have a good concrete foundation. On the right, here's another example of raw cement tank, and you see the rounded dome top. That's a good structural component for strength. You see the overflow, the outlet. Here's the inlet. So this is perhaps coming from our roof, and this is just showing you the wire mesh, this is part of the design of the raw cement tank. In this case, they have a gravel foundation for this one, so that's another option as well for you. At the bottom, of course, here you have the undisturbed earth. So showing you these designs over and over, just getting you used to the different designs, but also you see the components of the design that are pretty much the same for each one of these. So they all have some type of access hatch, overflow mechanism. They have valves to make sure that we can control the outlet and so forth. They have some type of stone concrete base. It becomes important. And finally, here is another example of a cistern. All of the same components we've seen, just showing you the plan and profile view. So this side view, this is the plan. This is the profile view from both two perspectives, and then the top view is the plan view. So you see the access hatch here, the manhole. If we wanted to make this an underground tank, this is a sleeve here. We can insert a pump. I recommend using a hand pump. It uses only human energy and no electricity, so that's a good application. Here is the spot for our roof washer, our first flush system. But again, you see all the same components that we saw before. All right, what we want to get into now is sizing the cistern. So I'm going to open up a spreadsheet that we use for rainwater harvesting calcs. Very simple calculation, but we're going to look at how we can determine how to size the cistern, and that'll be it for our session 3. Okay, so here we are, and this is our rainwater harvesting design worksheet. This is from a project that we worked on in Agbede, the Juicy Drop-In district of the Asante region. And we are going to take a look here at some of the basic inputs for this spreadsheet and how we can use this to determine the size that we need for our rainwater harvesting system. So what we're going to look at are, of course, we're assuming we're dealing with roof water harvesting, and so in order to provide adequate storage, we need a design of our cistern that accounts for that based on the amount of available rainfall that we expect. And so there are three main points that we need of data, of information that we need in order to have a good design, or in order to appropriately size our rainwater tank. And that is the amount of monthly rainfall. And I'll give you some insight on where you can find that in a second. You need to be able to calculate the potential rainfall supply that's available each month. That's the same calculation we've done 2 or 3 times already. And you need the amount of water that's likely to be consumed by the family. And this is the demand. All right, so you need basically the supply of rainfall. You need to be able to calculate the supply of rainfall, you need the amount of monthly rainfall, and then you need the demand. And based on those things, you can size your rainwater harvesting tank for the particular system that you are looking for. So where can you go to find data on your average monthly rainfall? You can go to the National Weather Agency if one exists. You can go to perhaps the Ministry of Agriculture. Sometimes the military will have that type of information. You go to airports, they often keep records of weather, things of that nature. And like we've always said again, if nothing else, if all those things fail, you can go to an elder in the area and get insights on the amount of rainfall for the various seasons. What I've done is, if I go to the internet, done a quick search here, and I found a website where we can choose a country and get rainfall data from various locations. So I'm going to select Ghana, and we have various stations here, and here is Sunyani, which is in the Bonahafo region. So we click here, and I want to look at percentile and year data, and let's just go back a few years, so 2014, 2013, 2012, 2011, and 2010. So we're going to look at the cumulative rainfall for those years and see what we get. And so here we are, we have the rainfall trends there. And so you can see clearly the 2 rainy seasons by the large jumps in the precipitation. So again, this is total annual precipitation. That's why it's highest in the end of the year. So we basically have little to no precipitation in the beginning of the year because we're still in the dry season, we're in the Harmattan. And you see rainfall starts to pick up here, and then it jumps up. The total rainfall jumps up in around the end of May or June. We've hit the rainy season. All right, so total rainfall jumps up then it starts to kind of steady out. So after it jumped up a while, it jumped up, then it kind of steadies out for a few months. So now we're back into our second dry season of the year, and then it jumps up again, not as much as the first one, but it jumps up again around October, and then starts to level out towards the end of the year. So this is one website, just one that I found, where you can find some precipitation data like this, and you can download it for each month. This is the total rainfall, but you can actually get it month by month. So for this worksheet, it's pretty straightforward. All of our inputs are in orange. So if we just go down the list, the first thing we have to input is the number of users. So the assumption here, again, is we're in a rural area, we're in the bush, we're in Africa, and we are building a rainwater harvesting system for our homestead that we're living on. So perhaps there are 5 people, perhaps it's our family, and there's 5 of us, and so therefore the number of users we're going to do is 5. Right? It doesn't particularly matter whether they're children or not. Children are going to use less water, but you still want to design it as if the children are adults, because one day they will be adults. And so you want to design it for that potential capacity. Or if you're in a situation where you just get started, maybe you have 1 child, maybe you don't have any children yet, but you plan on having children, then you definitely want to size your system for that future condition. So if you plan on having 4 or 5 children, then you need to go ahead and design your system for 8 or 9 people. All right, that's just best practices. Of course, it has to do with your budget, and we talked in the previous session about the options of phasing. So perhaps you start with a smaller system now, and as funds become available, you scale up. So that's another option. But this is our first input, the number of users. And for the example we're looking at now, we have a household size of 5, and this is our actual worksheet in gallons. So I'm going to get into this, but I'm going to show you another worksheet. But what I wanted to show you from this worksheet before we get into that is the rainfall data. This is for Ghana. And so again, you can see very clearly those two peaks that I was just talking about. So these are our two rainy seasons here. So the one peaked in June and the other in October, and then going into the Harmattan and the dry season, the first dry season in December, January type of time frame. So wanted just to show you that and give you an idea of what that looks like. So what that means is that water supply in this particular location is not evenly distributed throughout the year. If it were evenly distributed throughout the year, perhaps it will be more or less around this 1,000-liter mark every single month. But that's not the case. We have the wet season and we have our dry season. So we have to adjust our design accordingly. And this worksheet allows us to do that. So let's go over to the next tab. It's the same thing, but it's in liters instead of in gallons. Because outside of the United States, most of the rest of the world operates in the metric system. So we're going to do this example in the metric system. So here we are again. And this spreadsheet is set up, so I talked about the users, it's set up so that if you think in liters and you're using it in gallons, you can still use it. Or if you think in gallons and you're using it in liters, it's still helpful to you. So the grayed out values below here, these are the values in gallons. So that kind of gives you a gauge if you don't think in liters. So our daily demand for this is liters per user, per day, of course. For this particular dime, we're saying it's about 17.4 liters. All right, that's our daily demand of everything. That's everything. That's cooking, cleaning, washing, everything. Everything we would need water for. We're saying 17.4 liters per person per day. All right, so that's a good amount. Again, we're being conservative here. We're Africans, we're not Americans, so we don't waste water. And so 17.4 liters per user per day. And using those two numbers, we take our 5 users and multiply it by the number of liters per user. Multiply 17.4 by 5, that gives us a total daily demand for our household of 87 liters per day, right? Which is about 23 gallons per day for our five users. And we're still dealing with our same scenario. We have our 6 by 8 meter roof, so that gives us a 48 square meter roof area, projected roof area, which equates to about 516 square feet. All right, for our first flush, how do you design a first flush? Well, there's not a lot of hard science that goes into it, but just rules that have kind of been observed through time. And the rule that we have for designing a first flush system is that your first flush should be able to contain the first gallon for every 100 square feet of roof area. First gallon for every 100 square feet of roof area. And in liters, that translates to the first liter for every 2.45 square meter of roof area needs to be discarded. So that means if your roof area is 2.45 square meters, then you need to discard 1 liter of the first liter of rainwater, right? So for our roof, since we have a roof area of 48 square meters, that means that we need to discard or flush the first 19.8 liters of rainfall that we get, because that's going to have the worst debris and so forth in it. So we're going to get rid of that. So that's about a little over 5 gallons that we're going to just discard, and we're not going to let that get into our tank. I'm assuming an efficiency of 85%, and we can, you can adjust that as you see fit. And we use the system every day. So this value is basically 365 divided by 12. And so that gives us about 30.4 days a month. So that's an average. That's basically, we're using that as our average month. So that means that we're using this system every single day. A little bit different if this was a school or something like that, where it's only really used 5 days a week. Nope, we're using this every day a week, all year. All right, so those are the first set of inputs. The next set of inputs is our yearly rainfall. So we want to not only have that, okay, in this particular region we have 1,032.5 millimeters of rain. That's only going to get us so far for our design. What we really need is we need the monthly distribution of rainfall. So here is what I have, and this is a different region than Ghana. So this doesn't have the dual peak, like the dual wet season. This is just a single wet season and a dry season, all right, which is typical to a lot of other places as well. So we see our wet season, really November through March, very, very wet, and then the rest of the year it's basically pretty dry, especially in June and July. It's very, very dry there. And so those are all the inputs. And so what do we do with those inputs? Well, we take those inputs and the rainfall we use, first off, we can make a distribution. So that's one of the first things we've done here. So we see a plot here of this is basically the rainfall. So we get a lot of rainfall at the beginning of the year, drops off during the dry season, we have little to none, and then picks up again towards the end of the year. So this is our plot. So that's first off, it gives us a visual representation of what we're looking at. The second thing we do is we take the equation that we've been dealing with, which is volume of rainwater is equal to 0.8, our runoff coefficient, times the amount of rainfall in millimeters, times the projected roof area. And based on that, that gives us the liters of available water from our catchment. So that's what this column here is. Right? This is giving us, this is that V equals 0.8 RA equation for each specific month. Right? So you can see for the month of January, I've taken this annual amount of rainfall, 226 millimeters, multiplied it by my roof area, which is 48 square meters, and multiplied it by my efficiency factor of 0.8 or 80%. And that gives me this about, 8,700 liters that I can expect for this roof. And I've done that for every single month of the year, which tells me for the year, we can expect from our roof area, from our 48 square meters, just under 40,000 liters of water. That's in a year, all right? Based on 1,032.5 millimeters of rainfall. That's what that corresponds to. Next, what we've done is we said, well, that's not exactly the rain that will be going into our tank. That's not necessarily what's going to be available, because we're going to remove a portion of that rainfall from our system every time it rains. And what is that portion? That's our first flush, right? Because we're removing, in this case, is just under 20 liters of the available rainfall. That means that that water is not going to be a part of our system, right? It's going to go into overflow and it's going to go down a channel, but it's not going to be captured. So we're essentially treating it as if it's not used in the system. So we're subtracting that value off, and that's what we see in this column. So this column, we have gone in for every calculation here, we've subtracted the first flush volume in liters. Okay, next what we do is we calculate a cumulative runoff. So just like the picture, the chart we just looked at from the Weather Service, where it gives us a cumulative rainfall for the year, what we're doing here is we are calculating the cumulative runoff. So for January, it's exactly what it is. For February, it's the sum of January, February. For March, it's the sum of January, February, March, and so on and so forth, giving us this same, so we see these values should match, right? And this is the sum of the total amount of water that's available, and this is what we get. And at the end of December, this is how much our cumulative roof runoff is. That is the rain that has fallen on our roof that is available to us in our rainwater harvesting system. Our water demand is essentially the total daily demand in liters, 87 liters, times the number of days in a month. That gives us our monthly water demand. So in this case, it's about 2,650 liters per month, and that's going to be constant. And for the sake of our calculation, that's going to be constant. In the real world, we actually use a little bit more water during the wet season than I should say we use less water in the dry season because it's less available. Or at least you should use less water in the dry season. So that's a little nuance there, but for the purpose of this calculation, we're going to assume that it's constant year round. And then what we've done is we've calculated the cumulative demand, right? So in January, it's this value. In February, it's the sum of these two values. In March, it's the sum of these three values, and so on and so forth. And finally, we have subtracted the runoff here from the demand, and that gives us these values. And then I have here is 14,500 value highlighted. So let's look down at this next chart to see what we have here. So the blue bar chart, this represents the cumulative roof runoff for the year. So it continues to go up because it's cumulative. So basically what we see here is we have, a little bit of rain in January, a little bit of February. It jumps up in March, and it stays pretty constant in April, May, June, July. It stays pretty constant. Then it starts to jump up again. And again, this is not from the previous one. This is not from the one in Ghana. This is from this system. So we would expect it to be constant between May and September because we get very little to no rain. So that's exactly what we see here. It's basically constant from the end of April. It goes up a little bit from April to May, but it's basically constant from May all the way to September, which is what we expect because we don't get any rainfall during this period of time. So it's constant there, and then it starts to go up again. You see at the end of the year our cumulative rainfall. So that's the blue that we see there. Then this one in green, this is the cumulative demand, which of course we know just goes up and up and up and up and up. So what we're concerned about is the volume of storage above our demand. We want to be able to store a certain amount of rainwater above our demand for use during the dry periods of the year, right? So it's nothing, during the wet part of the year to say, oh, we have so much more rainwater above our demand. But what's important is how much of that can we actually store. So this chart tells us that. So looking at this chart, we want to look for the largest difference between the cumulative runoff and the cumulative demand. And it may be a little difficult to do it based on this chart, but it actually occurs in March. And where does it occur? How do I know that? Because of this. This is what tells me that. So see, we here in March, this is where our largest difference between those two curves is found. This is about 14,500 and some change liters. And so that is the size that we should size our tank for, right? Because if we size our tank for that amount, then that will be sufficient to store enough water to last us through this dry period here. So if you can see this, let's see if I can make the screen smaller so you can see both charts. Yes, a little too small. All right, so if we see both charts here, so again, this is the rain trend. So we've got water up through April. We got rain up through April. So we want to be able to store that capacity here. And that storage that we have from January to April, we're going to use that from May to September when there's no rain. And we're going to use that rain. And you see, as we get to September and October, we have very little water left because our consumption is getting pretty much up to our storage capacity, right? So you can imagine this blue above, this is our storage capacity. So as we get over here to September, we get really close. In October, we're getting really close. Actually, we hit the mark here in October, but then the rain comes back. And so then we start to store water again. Right? So this is how our rainwater harvesting system works. And this is how we can determine how much water we need to do. All right, so that is our spreadsheet, and it gives us the required tank size for our particular situation. You see how it varies with the amount of rainfall, varies with the roof area, varies with the required tank size.
Look, I got my blue flag, red, black, and green. Same old material, just change the color scheme. Different lyrics, same beat, change the theme. But no matter the song, it's still 100 I put on. No kidding, like my put-out game strong. I'm pushing my pull-up game strong. I ain't talking about no gym, I ain't talking about lifting weights and calisthenics. I'm talking grind and presentation. They say roll, hold it down, but y'all here. They tell them step his flow up like the Nile River. Well, I always been going that now direction. We look at your map, now tell me who sold you your perceptions. Cause I be on that upper Kemet, Lord Kemet. If you don't say it how I say it, know them girls did it. Which had my walk kinda off up on the New Balances, so I had to dust off on my eyes, and I brought that old thing back. I brought that old thing back. We want that old thing back. Got that old thing back. Need that old thing back. Want that old thing back. Want that old thing back. Got that old thing back. Want that old thing back. Need that old thing back. Need that old thing back. Yeah. Need that old thing back. Want that old thing back. Want that old thing back. Got 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 that old thing back. Need that old thing back. Look, my mama, my birthplace, my origin, my wisdoms, my wealth, my resources. A brother from the continent said I hate to disappoint, but this ain't like America's joint. But baby, that's the point. Look, you mean to tell me you don't find something wrong? How you love everybody else except your own? I find it funny how you leave for lack of money just to go to another country and find out where your stuff gone. Dedicate my life cause I'm made from ya. No matter what they say, I always love ya. From the waters to the lands. Kill my scars with your shea butter. You're more than shea butter. I know you're my source of strength. You're my source of strength. Yeah, and I know you're my source of strength. You're my source of strength. Want that old thing back. Yeah. Want that old thing back. Yeah. I'm gone. Whoa, whoa.
So hopefully, if you have been able to stick with me through this entire presentation, through all three sessions, hopefully you have a better grasp on what's required to design rainwater harvesting systems. As as water supply systems go, they are very easy compared to the other systems that are available. So this is definitely a do-it-yourself type of project if you're able to do that. So hopefully you feel a little more informed and empowered in doing that yourself. Setting up a design worksheet such as this is not difficult. So you can do something like this, hand calculations, whatever you need to do. But hopefully the idea of sustainability has this presentation and the whole Sustainability Summit has got you thinking about this idea of sustainability, and hopefully you're a little more empowered as it relates to your water independence as an African. And hopefully if you have questions, you will stick around for the question and answer session, or you can feel free to contact us at any time. Our website is www.nkalaenvironmental.com. We're for Africans only, so we hope to see you soon in the future. Until next time, Yabeshia.